of complex variable are straightforward to analyze, just the way we did the last two. For example, if we have this function, consider this function. If we have this type of function, now along the x-axis moving to the origin, okay, along the x-axis moving towards the origin from the right, we're going to get z is equal to x. And then for this other one, we're also going to get this bar is equal to x. Then if this is going to x, this is going to x. Okay, if we approach it in this positive way, we're going to get 1. That is a given part. If we approach it towards a negative, we're also going to get -1, which is also a good one. Then the two limits, when we put them together, will not exist, because this and this, they are not the same. Remember, all the one, when we follow it along a particular path, the horizontal, the vertical, and all of them, as all the answers were the same. But in this case, the answers are not the same. If you follow it along this path, you will get 1. If you follow it along this path where it says the negative, you will get -1. The x, when we say z, along the x is x. Along the y is minus, is I, right? It's IY. We have x in the form of x. Let me make it clear so that you will get it. Z is always x plus IY. That's what I'm saying. We approach this problem in the x direction. We're going to get our limit 1. If we approach this problem, and when we want to, if we approach this problem in the y, okay, we're going to get this and its conjugate. Okay, we're going to get z will be I this. What is this? This one will be I this. This one will be minus I this. Such that when you cancel everything, you get -1. Now, what I'm saying is that any limit that exists, no matter the path you approach it, it must always be the same. But now we approach this one in the x, we get 1. Approach it in the y, we get -1. It means that it does not exist. Is that clear now? Then this limit does not exist because they are distinct. So we cannot assume that the limit of the function f of z, as z tends towards this, is independent of the path. So even though we use the first two to show that no matter the path, we're getting the same answer, we cannot assume that limit of z function as it approaches towards a particular number is always independent of the path. The path plays a lot of role. Okay? So how do we solve the problem? We're going to solve the problem using this kind of definition, which is what is referred to as, we have to define a way of making sure that there must be continuity. And this discontinuity in terms of the path is as a result of what? It was a rational complex function. So if it's a rational complex function, the discontinuity must come there. So because of the discontinuity, we must find a way to make it to be continued. Okay? So what is the meaning of continuity in terms of a function? The first thing that we know to make sure that a function is continuous is if we take the function of that limit that we are looking for. For example, if this is f of z, and we say it is continuous at this point where z is equal to z of 0, then this statement must be true. F of that point where it is tending towards it must exist. F of that point where it is turning towards it must exist. That is the first point. The second point is, if we take the limit towards that point, okay, of that function, it must exist and it must be equal to the f of that function. For example, look at this particular example. If we consider this, now they say take the limit as z goes to I. It therefore implies that it means that anywhere you see z, you put I. Anywhere you put z, you see z, you put I. So anywhere you see z, you put I. In that case, we're going to get 3 all over what? 8. What is the meaning of that? It means that this function is always continuous at the point where z is equal to I, because that point, the limit exists. However, we want to look at the point where there's discontinuity. If we now take this denominator and we equate it to 0, it therefore implies that anything divided by 0 is what? Undefined. It means that if this denominator can be equal to 0, that means this function does not exist. So that is the point where we must find our continuity. So that is why we say, okay, let's take this denominator, equate it to 0, and find those points where when we put it here, it will become undefined. And if you do that, you're going to realize that z at this point, this z is, if it is positive or negative 3i, it therefore implies that the function will not exist. It's easily shown that these are the only point of discontinuity. Apart from that point, everywhere the function is continuous. So now, the question now is, state where this function is discontinuous. Can you state it? Then, hence, find the limit when f of z is equal to, when z is equal to I. Very straightforward. This one is more, right? So what is the point where this function is discontinuous? Somebody should answer me. What is the point where this function is discontinuous?
Okay, sir. Plus or negative 2i.
Correct. And then what is the
And
limit?
what? Sir, I didn't get you.
What is the limit when z goes to I?
When z goes to I, that it will be,
That is
I'm from that's I over I square plus 4.
perfect. Um, for which value of z is w equal to 1 all over z minus 1 defined? We just did something like this before, right? This one, is it a problem? It's straightforward, right?
Yes, it is.
Number 2, find the limit of f of z as z goes to I along the path A, parallel to the axis coming from the right, and then B, parallel to the y-axis. This one, we have nothing to do with k because we only have z and I. Is that one a problem? It's just exercise what we have done in class already. Then number 3, where is this function discontinuous? Find the limit for that. We will do this. This is your assignment